Hi everyone, my name is Neelu. I'm a PhD student at EPFL and I will present our work titled Say What Must Be Saved, Secure Context Switching with Sailor, which appeared at USENIX Security 2025. It is a joint work with my co-advisor Thomas Bourgeat and Guerney and Wojciech Ozga from IBM. You must have heard about context switching in your bachelor level OS class, where privileged software performs the context switch between two isolated security domains, such as two different processes, and the privileged software provides isolation guarantees that the data of one security domain does not leak to the other, as well as the one domain does not influence execution in the other. And this is achieved by correctly swapping all the architectural state during context switching. However, in practice, even in industry standard software, there are bugs in context switch implementations. And the reason for that is the ever-growing instruction set architecture manuals and hundreds and thousands of complex registers in the ISA state. The trend is the same across different architectures, whether it be ARM, RISC-V, or x86. Just forgetting to swap a single bit in those hundreds or thousands of registers can cause information leaks. So, spoiler alert, we also found some bugs in existing context switch implementations. For example, when running the Linux shipped with the StarFive VisionFive2 board, performance counters leak across user processes and can lead to timing channel vulnerabilities. Komodo, which is a formally verified security monitor software, it has proofs based on self-written ISA specification. But if those specifications are not kept up to date with the evolving ISA, the proven security properties do not hold, and as expected, the registers introduced with newer ISA state are not taken into account by Komodo. Keystone, which is also a security monitor, leaks ISA extension state such as floating point or vector extensions. Further, even for ISA extensions that Keystone does not support, for instance the vector extension, there are no checks to discover if those extensions are implemented by the platform and then proactively disable these extensions. So essentially, they can easily be leveraged by unprivileged adversaries to leak information. To find these bugs, we did not go and read those thousands of pages of Prose-style ISA manual PDFs, tempting as that may be. Instead, we leveraged the machine-readable ISA specification written in the Sail language and automatically generated tests to check if the context switch code swaps all that ISA state correctly. And thus, I present our tool Sailor, which takes the Sail specification and feeds it into ISLA, a symbolic execution engine for Sail. With ISLA, we can basically capture all the possible interactions that the execution of an instruction can have with the ISA state. For example, exceptions on floating point operations set a certain flag with a specific value, which denotes the type of exception that occurred. And if this flag is not cleared during a context switch, then information leaks. And then using that, we propose a systematic way to identify all the ISA state that must be swapped across context switching, using the output that we get from ISLA. Now, maybe you already know about Sail, but for those of you who don't, here's what it looks like. On the left, there is the Prose-style specification of the MRET instruction in the RISC-V ISA manual, and on the right side, there is the corresponding Sail specification. So as we can see in the Prose-style specification, XIE is set to XPIE, for instance. We can map that to the Sail specification when on line 5 we read that the MIE field in mStatus is set to MPIE. Then ISLA, the symbolic execution tool that I mentioned earlier, takes the sail specification along with an instruction and some ISA constraints and internally uses the Z3SMT solver for the symbolic execution of sail. And then it generates all the possible execution traces for the given instruction. For example, 264 traces are generated for the load instruction in RISC-V. Let's take a quick look at some of the traces that ISLA generated. For example, for the instruction to read the control and status register instaret, which denotes the number of instructions retired. When executed with supervisor mode privileges, two traces are generated. One that does not trap and successfully reads the register, which is shown on the left-hand side, because the instructions retired counter is enabled for access by supervisor mode in that case. And then another trace is generated on the right-hand side where we can see that the instruction traps because the counter access for supervisor mode is not enabled. Now to identify which ISA state to actually swap during the context switch, we basically look for channels that can be created to cause leaks. A simple example is if a security domain has the access to write a particular register and another security domain has the access to read that particular register, then this register can leak information, and so it must be swapped during the context switch. Here's the complete algorithm to identify all the ISA state that must be swapped. This algorithm is then repeated for each ISA state per privilege mode pair. To take an example, let's say your source security domain is executing in user mode and so is the target security domain. Then for the floating point rounding mode register, FRM, since the source security domain has access to write it with user mode privileges, and the target security domain's execution of all the floating point operation depends on the value of this rounding mode, not swapping this state during the context switch can affect computation integrity in the target security domain. So the algorithm marks this register to be swapped across context switches from user mode to user mode. To get the complete picture, we generate the traces from ISLA, and then we parse these traces to extract all the information in the format that we show in the tables on the left-hand side, which is then used as input, given as input to our algorithm, and then the algorithm produces a list of all the ISA state that should be swapped across context switches, as well as all the ISA state that we don't really need to care about. For all the instructions in a general purpose RISC-V CPU, 3 GB of traces are generated from ISLA, which takes about 20 hours for the symbolic execution. This is a one-time cost per sail model update and can be repeated daily or weekly to keep the results up to date with the evolving ISA. Then parsing of the traces and running the algorithm takes less than 10 seconds. Once we have the algorithm's output, we use it to check the security of existing context switch implementations. This can be done using simple utilities such as grep or code scanning. We also automatically generate some tests to check if the context switch swaps all the ISA state that our tool says it should. However, there are more applications for the algorithm's output. For example, implementing secure context switch code and then also using that those insights as a guide for designing new ISA extensions. For instance, the ISA state previously classified as not security sensitive must not become security sensitive with the introduction of this new extension. So this is essentially a question about backward compatibility. Further, newly introduced ISA state should not be security sensitive when the extension is disabled. As I already mentioned earlier in the talk, we analyzed three systems: VisionFive2, Komodo, the StarFive VisionFive2 board, Komodo, and Keystone. In VisionFive2, where we analyzed a switch between two different user processes. And in Komodo and Keystone, we analyzed a switch between two different operating systems and runtime that run with supervisor mode privileges. Reiterating through our results, on the VisionFive2 Linux, we found that performance counters are directly exposed to user programs. In contrast, upstream Linux only exposes these counters through the perf tool, which clears them appropriately. Komodo has this problem with self-written ISA specification being outdated, and Keystone lacks proactive checks for disabling unsupported extensions. To note here, it is not our goal to mount attacks with the bugs that we found, but we describe the security implications of not swapping the state in the paper. And we want to emphasize the goal of the tool to help enable identify all such state and then actually correctly swap them during the context switching. Future work on Sailor includes extending it for other ISAs like ARM, because Isla also can generate traces for ARM, using formal methods to automatically generate verified context switch code. For example, feeding the output that we get from Sailor into verification frameworks such as Serval. And finally, integrating Sailor with the CI/CD pipeline of existing systems for dynamically updating context switch implementations with the insights generated from Sailor as the specification evolves. In conclusion, we tackle an already well-known problem of secure context switching, which unfortunately still hasn't been solved because of the growing complexities of ISAs. We provide a solution to automatically analyze the ISA specifications and generate information on which ISA state must be swapped during context switching. Thank you so much for listening to my talk.